Alright, in our last video we looked at how to prepare acid chlorides or acyl chlorides. And the easiest way to do that is by starting with a carboxylic acid and then treating it with thionyl chloride. And we went over this mechanism briefly, but the key feature in this mechanism is you generate sulfur dioxide gas, which gets liberated out of solution and it drives the reaction to completion. And these acid halides are incredibly versatile intermediates. You can react them with water to go straight back to a carboxylic acid. You can react them with alcohols to go to esters. You can react them with amines to go to amides. You can reduce them to primary alcohols if you're using a strong reducing agent like lithium aluminum hydride. And then if you want to stop at the aldehyde, you can use a bulky reducing agent like lithium triterbutoxy aluminum hydride. And in this case, it will only reduce the acid chloride. It won't reduce any other ketones or aldehydes if they're present in your starting material. In addition, we looked at reactions with carbon nucleophiles. And we said that Grignard reagents, being the classic carbon nucleophile, are really strong. And so they'll add into the acid halide once. We'll get to a ketone, but then that ketone will react one more time with another equivalent of our Grignard to give us a tertiary alcohol. If we want to stop at the ketone, we need to use a bulkier reagent, like a Gilman reagent. And the Gilman reagent is an organocuprate that will only add in once and will stop at a ketone. It's too bulky to add further to a ketone. All right, so what I want to do before we go on to new material is just make a mini reaction map. And this mini reaction map I think is helpful for studying. And I like to do this just as a way of kind of reinforcing what reagents I need. So let's go ahead and put carboxylic acids over on the left, and we'll put our acid halide in the center, and then we'll try to kind of stagger functional groups around, and we'll make a mini roadmap and try to connect this in as many ways as possible. So I'll put an ester up here, I'll put an amide over here. And just to be thorough, let's put all of the different types of amides. So we could have a few different types of amides. And we could also have a primary alcohol. We could have an aldehyde. We can have a tertiary alcohol. And we can have a ketone. All right, so if you remember from last term, we had a reaction map. If you wanted to, you could even incorporate all of these into your previous reaction map. All right, so let's take a look at the first one. If you remember, we can go from a carboxylic acid to an acid halide by using thionyl chloride. So SOCl2 is the reagent, at least that's shown in the Klein textbook. There's other reagents that work as well. However, we're going to focus on this one. Keep it simple. And then if we want to go backwards, all we really need to do is water. And oftentimes you just add a small amount of acid to ensure that your final proton is present on your carboxylic acid. So having a lower pH does help there. All right. So we can interconvert back and forth between carboxylic acids and acid halides. Now let's just go clockwise around. So for example, if I want to go from an acid chloride to an ester, all we need is an alcohol and we need pyridine. And if you remember that pyridine is one of our non-nucleophilic bases, it's really just acting as a sponge for protons here. So it's just absorbing any extra protons to avoid unwanted chemistry. All right, the next one, if we go clockwise around, is forming our amine. And like I said, the nice thing with amines is we don't need any additional base because the amine will act as both your nucleophile and your base. And we can do something similar with all three of these. The only difference between these is whether or not you're using ammonia, a primary amine, or a secondary amine. So for example, if you use a primary amine in excess, you can get an amide. And same thing here. you can get an amide this way. So it really just depends on which amide you want. But in either of these situations, we're going to have to use excess because it's acting as a base. All right, next one. If we want to go from our acid halide to a primary alcohol, we need to use a strong reducing agent. So something like lithium aluminum hydride in excess. And then we want to treat this with water as our final proton source. So that works pretty well. Let me move these around just a smidge more so we have some more space. We said that this intermediate during this process is an aldehyde, but this reaction goes uncontrollably. So if we want to stop at the aldehyde, we have to use a bulkier hydride source. And if you remember, this hydride source, I'm going to actually write it on its side because it's a little long, is lithium triterbutoxy aluminum hydride, which can be written LiAl, and then in parentheses OR, close parentheses 3H. And this is so bulky that it can only reduce the acid chloride. It can't reduce the aldehyde or ketone. All right, next one. If we want to go to a tertiary alcohol, we can react this with something like a Grignard reagent, so RMgX. And in this case, we are going to add it in excess because it's going to add uncontrollably anyways. So even if we only put in one equivalent, we're going to get a substantial amount of the tertiary alcohol, so we might as well push it to completion. All right, then step 2 is to treat this with water. All right, last but not least, we said if we want to go to the ketone, we can treat this with a Gilman reagent, and that will stop at an intermediate, or at a ketone intermediate, because it's so bulky. So R2CuLi. So like I said, when I'm studying for this, it's a lot of reactions, but creating a reaction map is a really good way of preparing for exams and quizzes, and then just being familiar with what reagents you need. All right, so that's where I'm going to stop now. When we come back, we're going to look at preparation and reactions of acid and hydrides.